Okay, this final lab is on substitution reactions. Hopefully you can see over here that we have an alcohol, and it's a tertiary alcohol, which is being treated with an acid, and it's going to give you the corresponding tertiary alkyl halide. In some ways, this reaction is similar to the reaction that we ran for the elimination last week. And so for that reason, and I'm going to just, first of all, highlight, compare and contrast the similarities and the dissimilarities. Let's say you would have treated it with the same substrate with H2SO4 or H3PO4. Now the Lewis dot structure of H3PO4 is going to be this. Of course, you have your lone pair of electrons. And so, mechanistically speaking, recall that the lone pair of electrons are going to pick up the proton. The H2PO4 negative leaves. So you end up with the two methyls, OH2 with a positive charge. And now you have to ask, should you remove water first, or what should happen? In this particular case, since it's a tertiary center which is holding that leaving group, you would say absolutely the carbocation that is going to get generated is super duper stable, and that is the reason why water would leave. It will give you the tertiary carbocation, and then since we are heating the reaction up, the H2PO4, which by the way is pretty bulky, and hopefully you can see that that negative charge doesn't quite stay on one single oxygen, so it's not localized. Rather, this conjugate base has been stabilized by, you guessed it right, resonance. So you can draw resonance structures that look like this, and then this can come back, and you could have done that for any of the other hydrogens as well. So realize that the conjugate base is resonance stabilized, it's big and bulky, so this is a base, it's a stable base, it's not a nucleophile. What does that tell you? That tells you that you would never, ever show the attack of the oxygen attacking directly at the carbon with the positive site. So what this H2PO4 negative is really looking for is just abstraction of a proton so that it can become phosphoric acid again, and that's it. So that's what it's going to do. It's going to pick up the proton, electrons will move between the two carbons, and your final product should look like an alkene. The same thing can happen on the other side because there are really 3 beta sites like that. And hopefully you can also envision and predict that it's the second structure that I drew which is going to be your major product. Reason being, this is going to follow the Zaitsev rule, according to hyperconjugation as the basic principle. Recall what we learned in chapters 7 and 8, that more substituted alkenes are more stable. So essentially, elimination reaction of that tertiary alcohol is going to give you the more substituted alkene as a major product. The other one is going to be the minor product, and that is the reason when you run the GC of that, you will see 2 peaks out of this. Now, let's compare this exact same thing to what would happen if the source of the protons is HCl, not H3PO4 anymore, but HCl. So the first step is going to be exactly the same. And that's what I'm going to show you now. The first step is going to be exactly the same, where the lone pair of electrons will pick up the proton, Cl will leave. Okay? Now, once that happens, you can show, of course, the OH2 getting formed. Again, you ask yourself the question, should I form the carbocation? And indeed, this is the tertiary center, so absolutely, that's a very stable situation. Go ahead, form the carbocation. That's what you get. Now the question is, what is possible? What is likely? Whether the Cl negative, because it doesn't have any resonance and it does have all the negative charge with it, so does it behave as a base and would rather pick up the protons, or would it attack as a nucleophile? And in this particular case, majority of the reaction goes through a substitution reaction, but realize depending on the reaction conditions, there will be an elimination reaction that will take place that will compete with your substitution reaction at all times. So chloride is an example of a situation which is basic as well as nucleophilic. But in this particular case, because the corresponding conjugate acid, HCl, is fairly strong, you would consider that the corresponding conjugate base is somewhat weak. But nevertheless, it is a nucleophile, and that's going to attack and give you the tertiary halide as your product. Like I said, depending on the reaction condition, if you overheat, the last 8 years I have seen that only once, but it's a possibility. If you overheat the reaction too much, there's a possibility that you will have the elimination product in this case, and your IR would be reflective of that, because you will see vinylic hydrogen. You will also see carbon double bond carbon at 1600 and the H at the 3000. So if you see those peaks in your IR of the product, that's reflective of the fact that to some extent some of your yield was lost as the corresponding alkene, and it is a low boiling product, so since you're running this reaction as an open system, you're going to lose that yield. All right. So in terms of the handout that we have provided you, let's quickly go over the reaction conditions. You will begin with making a hot water bath. So in a group of, you are going to, by the way, work in the hood again. So you will begin by making a hot water bath. That hot water bath should be somewhere around 70 to 80 degrees almost. So if I were you, the way I would set it up is I would get the beaker. I would get the beaker rather than a complete water bath, and set up your hot plate. That's my beaker. Fill it about halfway through, because that way you're going to save some energy. Just heat what is required. And when you get the first bubble, so set it up the first thing while another partner should go weigh out, the reagents. One of you should go and set it up. And when you do that, essentially make sure that you just wait for that first bubble. The moment you start seeing 1 or 2 bubbles go up, that means it just got to boil. Turn off the heat and just let it stay there. So maintain it while the rest of your alcohol and everything else is being collected. So you're going to start with a large test tube, and you're going to add 5 milliliters of 2-methyl 2-butanol. Now you will put that in the test tube. Make sure you put a stir bar in there. To this test tube, add 5.5 milliliters of concentrated HCl and just mix it well. You want to mix it well because if they are not, then the reaction is going to take place at the interface, and you really want the entire bulk of your reagents to go through the reaction. And at this point of time, even though step number 4 says turn off hot turn hot plate off and add the test tube to the hot water bath. Recall, we had gone up to the boiling temperature, and then basically it was just settled in there. And if you notice, the temperature around then is approximately around 80-ish, is what the temperature would look like. Now at this point of time, your reaction mixture should look homogeneous. This should look homogeneous. And when you insert it in the water bath, so now you're going to place your test tube in the water bath, you will begin to see two distinct layers within the system. Those can start getting formed as quickly as about 3 minutes to about 12 minutes. So this is the time on an average that we have seen, depending on your water bath temperature, this is the time that it takes for that product to get generated. Now, one word of caution. If your hot water bath is too hot, if it's more than like a 90 degrees Celsius, some of your product can get volatilized off. So if you start seeing bubbles forming here and bubbles leave, that's not a good sign. You might want to cool down your water bath a little bit before you insert. So somewhere around 72, 80, 82 is a good temperature for this reaction, but you don't want to lose your material. So stick it in there for about 10 to 12 minutes. That's the maximum. Another way that you should monitor this reaction is that you can basically pay attention to the size of the product. So if in the beginning, let's say you started seeing a top layer form, okay, and as 2 minutes passed, maybe this layer kind of decreased in size. Stop your reaction, because probably your water bath is too heated up, and you're actually losing your material. So it's no point pursuing that. Whatever had to form did form, and basically you should just focus on extraction of that material now. Okay, this particular product, again, you can check for the density in terms of what the density numbers are, and go with that. Otherwise, basically, it's the top layer that we are after. So what you want to do is you want to transfer that into 10 milliliter measuring cylinder and go for the top layer. So collect the top layer in a beaker. Now, when you do that, I would then ask you to add a small amount of anhydrous K2C2O3. Realize why we are doing that. And you can use, if you don't want to use a beaker, you can absolutely use a small test tube. Either or will work. Realize why we are using K2C2O3. K2C2O3 is essentially a basic compound, and with any amount of traces of acids, irrespective of the source of proton, it basically gives you CO2. So when you add K2C2O3 to this reaction broth, any traces of HCl are going to be removed, and you're going to end up with KCl, H2O, and CO2. Now, you will need 2 and 2. Now, you will see, of course, when you add the K2C2O3, if you did a good job with the extraction method, that means in isolating the two layers, separating those two out. If you did a good job with that, and there was no HCl that was present, no amount of traces of aqueous layer, then you will probably not see any effervescence. On the other hand, if you did see bubbling, that means that some traces of the acid were there. So now you will have a little bit of water and KCl, and of course your product. So now you have to take the time to separate out the water and carry out an IR on your final product. So at that point of time, I usually ask you to look for an IR, run an IR. So if you saw bubbling, that would mean that water did get generated. So what you can do is then set up your short pad distillation. So here's your round bottom flask, which is the 25 milliliter, which is being connected to a still head, a thermometer adapter, and a thermometer. That's your elbow joint. And it is connected to another round bottom flask. And you will see that as you go through the short path, you're going to collect the fractions between 70 to 85. We say 70 to 85, but again, it really depends on where your thermometer is. Your thermometer should be placed at that Y junction, right at the diversion. And you would separate out your product. You will then go ahead and take the yield of that. And you will also do a IR on that. In addition to that, you would be running a chemical test, which I'm going to talk about in a second. But the three things that we would look for is yield, IR, chemical test. Now, if you did not see any bubbling, that means you should not have any water molecule. So then you can go ahead and treat it, as a dry compound, and take the IR and get the yield and do the chemical test. Let's talk about the chemical test now. So you started with a tertiary alcohol. You end up with a tertiary halide. It's in the nature of alkyl halides that when they are treated with 1% solution of silver nitrate, they generate a precipitate of silver chloride or silver halide, depending on what your halogen atom is. So that's the chemical test that you're going to be running. You're going to take a test tube, one test tube for the starting material, so let's call it A. So that's going to see the alcohol, maybe 2 drops of the alcohol, 2 to 3 drops of the product. You can add a little bit of acetone, so 0.5 milliliters acetone, just to solubilize, just to keep the phase the same, acetone in both of these. And then add about 5 drops of the AgNO3 that is provided. It's a 1% solution. You will add to both of these. You will notice that it's the product that gives you the thick white curdy precipitate, and the starting material does not give you any precipitate. And the negative test for the alcohol and the positive test for the product is a clear indicator that the reaction did go through, and we have actually in fact substituted the OH with the Cl. If you wanted to make sure, of course, IR is going to serve as a pretty characteristic evidence that there's no double bond in there. But if somebody wanted to, and they, do like a KMNO4 test on this product, KMNO4 is not going to work because there's no double bond. So realize everything that you ran last class for the elimination, that still might be applicable for this case. We are going to go with the positive silver chloride test though in class. All right, see you in class.